These are the answers to the AP Chemistry packet that covers topics 7.1 to 7.5. On this slide, you can see Unit 7 at a glance. Unit 7 is entitled Equilibrium. In this video, we will take a look at Topic 7.1, Introduction to Equilibrium, Topic 7.2, Direction of Reversible Reactions, Topic 7.3, Reaction Quotient and Equilibrium Constant, Topic 7.4, Calculating the Equilibrium Constant, and Topic 7.5, Magnitude of the Equilibrium Constant. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Topic 7.1, Introduction to Equilibrium. Here are some essential knowledge statements from the AP Chemistry course and exam description. Many observable processes are reversible. Examples include evaporation and condensation of water, absorption and desorption of a gas, or dissolution and precipitation of a salt. Some important reversible chemical processes include the transfer of protons in acid-base reactions and the transfer of electrons in redox reactions. When equilibrium is reached, no observable changes occur in the system. Reactants and products are simultaneously present, and the concentrations or partial pressures of all species remain constant. The equilibrium state is dynamic. The forward and reverse processes continue to occur at equal rates, resulting in no net observable change. Graphs of concentration, partial pressure, or rate of reaction versus time for simple chemical reactions can be used to understand the establishment of chemical equilibrium. The diagram at right represents a sample of water in a sealed flask at constant temperature. The arrows in the close-up view show that water molecules undergo two opposing processes, evaporation and condensation. This can be represented by the following equation, with liquid water on the left and gaseous water on the right, separated by double arrows. The double arrows in the equation indicate that the forward process, evaporation, occurs from left to right, and the reverse process, condensation, occurs from right to left. At equilibrium, these opposing processes occur at the same rate. Another example of equilibrium occurs in an aqueous solution of CO2 as shown below. In a bottle of soda, molecules of CO2 are entering and leaving the solution at the same rate. Another example of equilibrium occurs in a saturated aqueous solution that contains undissolved solid, as shown below. In a saturated aqueous solution that contains undissolved solid, solute particles are entering and leaving the solution at the same rate. Many chemical reactions can achieve a state of dynamic equilibrium in which the forward reaction, from left to right, occurs at the same rate as the reverse reaction, from right to left. Question 1. Consider the decomposition of the substance A2X4, which occurs according to the following equation, in which 1 mole of A2X4 decomposes to produce 2 moles of AX2. A sample of A2X4 is added to a previously evacuated rigid reaction vessel. The partial pressures of each gas are monitored over time, and the data are shown in the graph below. Part A. Use the information from the graph on the previous page to fill in the missing information in the data table below. So we start out at time equals 0 seconds, and so from the graph we can see that the initial pressure of the reactant, A2X4, is 8 atmospheres, and the initial pressure of the product, AX2, is 0 atmospheres. Now at 10 seconds, we can see from the data in the table and the graph that the pressure of the product, AX2, increases to a value of 2.8 atmospheres, and the pressure of the reactant, A2X4, decreases to a value that looks like it's just above 6.5 atmospheres. If we consider the stoichiometry of this equation, we know that 1 mole of A2X4 is consumed for every 2 moles of AX2 that is produced. Let's focus on the change in pressure during the first 10 seconds of the reaction, and the change in pressure should be proportional to the change in moles for this balanced equation. So the pressure of the product AX2 increases by 2.8 atmospheres. Therefore, the pressure of the reactant A2X4 should decrease by half that amount, or 1.4 atmospheres. So 8.0 minus 1.4 is equal to 6.6 atmospheres, which we can read from the graph. At 20 seconds, the pressure of the reactant A2X4 decreases to a value of 5.6 atmospheres. The pressure of the product AX2 increases to a value that is just under 5 atmospheres. Again, let's take a look at the change in this 10-second interval and relate it to the stoichiometry in the balanced equation. So in this 10-second interval, the pressure of the reactant decreases by 1.0 atmospheres. The pressure of the product should increase by twice that amount, or 2.0 atmospheres. So 2.8 plus 2 is equal to 4.8 atmospheres, which is what we see on the graph. Now, at 30 seconds, the pressure of the reactant and the product can be easily read from the graph because they're exactly on the line at the whole number. So the pressure of the reactant A2X4 decreases to a value of 5 atmospheres, and the pressure of the product AX2 increases to a value of 6 atmospheres. Now, if we look at that 10-second interval, again, relating this to the stoichiometry and the 1:2 mole ratio between reactants and products, we can see that the reactant, the pressure decreases by a value of 0.6 atmospheres, and the product increases by twice that amount, or 1.2 atmospheres. Okay, now let's take a look at 40 seconds. We can see from the table that the pressure of the product AX2 has increased to 6.4 atmospheres, and the pressure of the reactant A2X4 has decreased to a value that is just under 5 atmospheres. If we take a look at the stoichiometry and focus on this particular 10-second interval, we can see that the pressure of the product increases by 0.4 atmospheres. Therefore, the pressure of the reactant would decrease by half that amount, or 0.2 atmospheres. So 5 minus 0.2 is 4.8 atmospheres, which we can see from the graph. Now at 50 seconds, the pressure of the reactant A2X4 is 4.7 atmospheres, and the pressure of the product AX2 is just above 6.5 atmospheres on the graph. So the change in the reactant is, it decreases by 0.1. We expect the product to increase by 0.2. So 6.4 plus 0.2 is 6.6, and we can see that from the graph. Now, moving on to 60 seconds. The pressure of the reactant A2X4 is just above 4.5 atmospheres, let's say 4.6 atmospheres. And if we focus on the change, that is a decrease in that 10-second interval of 0.1 atmospheres. We expect the pressure of the product to increase by twice that amount, so it should go up by 0.2, and 6.6 plus 0.2 is 6.8, and we can see that from the graph. Now, from this point onward, the pressure of the reactant stays the same at 4.6, and the pressure of the product also stays the same at 6.8. So we have now reached equilibrium because the amount, in this case the pressure of both the reactant and the product, remains constant over time. So let me remind you of a couple of the essential knowledge statements. So this first one that I have highlighted on this slide says, when equilibrium is reached, no observable changes occur in the system. Reactants and products are simultaneously present, and the concentrations or partial pressures of all species remain constant. And we can see that very clearly both in the graph and in the table, that from 60 seconds onward, the partial pressure of the reactant and the partial pressure of the product are no longer changing over time. And then the other essential knowledge statement that I have highlighted on this slide says graphs of concentration, partial pressure, or rate of reaction versus time can be used to understand the establishment of chemical equilibrium. So here in this graph, it's partial pressure versus time. But then I will show you in part D of this question a graph of rate of reaction versus time. All right, here is part B, and we've already talked about this in this video. At what point in time during the experiment did the reaction reach a state of equilibrium? Justify your answer. So here we can see, as I've highlighted on both the graph and the table, that the answer to part B is the reaction reached a state of equilibrium at 60 seconds. And the justification is because after that point, the pressures of the reactant, A2X4, and the product, AX2, remained constant over time. Now, in part C, I'd like to take a look at the beginning of the experiment. During the first 30 seconds of this experiment, this is before equilibrium has been reached. So let's focus on the first bullet point. It says the partial pressure of A2X4, again, that was the reactant. It began, as you can see highlighted on the graph, at a partial pressure of 8 atmospheres. And then at 30 seconds, the partial pressure has decreased to 5 atmospheres. So the partial pressure is decreasing. Now I'd like you to recall what you learned back in Unit 5, kinetics, about the relationship between the concentration of the reacting particles and the reaction rate. So the rate of the forward reaction, how is that changing in this 30-second interval? Well, since we know that the partial pressure of A2X4 is decreasing, that means that the concentration of that chemical is decreasing in the reaction vessel. So as the concentration of a reactant decreases, there should be a lower frequency of collisions and a slower reaction rate. So the rate of the forward reaction is decreasing in this 30-second interval. Now let's switch over and talk about the product, AX2. So as you can see highlighted on the graph, the partial pressure of AX2 starts out at 0 and then increases to 6 atmospheres. So it's definitely increasing in this time interval. And then now they're talking about the rate of the reverse reaction. So the reverse reaction would be going from right to left instead of from left to right. And in the reverse reaction, AX2 particles behave as reactants if we're going backwards from right to left. So in that time interval, since the partial pressure of AX2 is increasing, the concentration of AX2 in the reaction vessel is increasing. There should be a higher frequency of collisions and a faster reaction rate for the reverse reaction. So to summarize part C, in this first 30-second interval, the partial pressure of the reactant is decreasing, and the rate of the forward reaction is also decreasing. And in that same interval, the partial pressure of the product is increasing, and the rate of the reverse reaction is increasing. So now on to part D, where you can see on the top, it's a graph of pressure versus time, but on the bottom, you can see a graph of reaction rate versus time. So here's what part D says. A plot of the reaction rate for the forward reaction, that is going from A2X4 to AX2, that graph is already shown. So in other words, you can see that the reaction rate starts off pretty high, gets a little bit lower, and eventually levels out to a non-zero value. Draw a curve on the graph to show how the rate of the reverse reaction changes over time. So this is the interval in which equilibrium has been achieved between 60 seconds and 100 seconds. And the essential knowledge statement says, when equilibrium is reached, no observable changes occur in the system. That's what we can see on the top graph on this slide. But then that other essential knowledge statement says, the forward and reverse processes continue to occur at equal rates. So we need the rate to eventually be equal at equilibrium, the rate of the forward reaction and the rate of the reverse reaction. So therefore, the reverse reaction starts out at 0 because in the beginning, there are no particles of AX2 in the reaction vessel. So the reverse rate is 0. That's going to steadily increase until eventually the rate of the reverse reaction is exactly equal to the rate of the forward reaction. So it increases and eventually matches the rate of the reverse reaction. So at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. All right, moving on to a new question in the packet. This is question 2, and now we're talking about a different system in which A, the reactant, is transformed into B, the product. So question 2 says the following. Consider the system involving a reversible chemical reaction as described by the equation above. Decide if each of the following statements regarding equilibrium are true or false. So the first statement says, if the rate of the forward reaction, so from A to B, is greater than the rate of the reverse reaction, from B to A, then equilibrium has not yet been achieved in this system. Well, that's definitely true because if equilibrium has been achieved, then the rate of the forward reaction would be the same as the rate of the reverse reaction. So if that's not happened yet, then equilibrium has not yet been achieved. The next statement says, when equilibrium has been achieved in this system, the partial pressure of A, the reactant, should be equal to the partial pressure of B, the product. And that is not necessarily true. As you can see from the graph on the top part of this slide, equilibrium was achieved, but the partial pressure of the reactant was not the same as the partial pressure of the product. So again, statement number 2 is not necessarily true, so we're going to say false. The next statement, when equilibrium has been achieved in this system, the partial pressures of A and B should not change over time. Yes, that's true. They're going to remain constant over time. When equilibrium has been achieved in this system, the particles of A and B should no longer collide or react with each other. That's false. Equilibrium is a dynamic system in which the reactants are converted to products and the products are converted to reactants at the same rate, but they're still happening, as in the reactions are still occurring in opposite directions. They're still colliding and reacting. And then the last statement, when equilibrium has been achieved in the system, no observable changes will be detected, giving the appearance that nothing is happening in the reaction vessel. And yes, that is true. So again, question 2 was kind of a summary of some of the information that was presented in the essential knowledge statements in this topic, as well as in the example problems in this packet. All right, moving on to the next topic. This is topic 7.2, direction of reversible reactions. Here are some essential knowledge statements from the AP Chemistry course and exam description. If the rate of the forward reaction is greater than the rate of the reverse reaction, then there is a net conversion of reactants to products. And now let's flip that around. If the rate of the reverse reaction is greater than the rate of the forward reaction, then there is a net conversion of products to reactants. An equilibrium state is reached when these rates are equal. So what we're going to do in question 3 is compare the amount, in this case the concentration, of the reactants and the products at 2 different time intervals. And based on how those concentrations are changing, then we can decide if there's a net conversion from reactants to products or a net conversion from products to reactants. Okay, let's take a look. Question 3 says, consider the reaction between hydrogen, H2, and iodine, I2, to form hydrogen iodide, HI, as represented by the equation shown above. Different experiments were performed and were carried out at the same initial temperature. So we have a table with time 1 and time 2. Now the reactants are hydrogen and iodine, and so those concentrations at time 1 are 2 molar for hydrogen and 3 molar for iodine. The product is hydrogen iodide, or HI, and the concentration at time 1 is 1 molar. Now let's see what happens when we go from time 1 to time 2. So the reactants went from 2 molar and 3 molar to 1 molar and 2 molar. So the concentration of the reactants decreased, and in that same time interval, the concentration of the product, HI, increased from 1 molar to 3 molar. So therefore, we have a net conversion from reactants to products in this time interval. Therefore, the rate of the forward reaction is greater than the rate of the reverse reaction. Now let's move on to part B of this question. So at time 1, the concentration of the reactants, hydrogen and iodine, are 0.1 molar for hydrogen, 0.2 molar for iodine. The concentration at time 2 of the reactants is 1.0 molar for hydrogen and 1.1 molar for iodine. So in that time interval, the concentration of the reactants increased. And in that same time interval, the concentration of the product, HI, decreased from 9.5 molar to 7.7 molar. So if we have an increase in reactants and a decrease in products over that time interval, there must have been a net conversion from right to left or from products to reactants. So the rate of the reverse reaction in that time interval is greater than the rate of the forward reaction. Okay, now let's take a look at our next topic in this packet. This is topic 7.3, reaction quotient and equilibrium constant. Here are some essential knowledge statements from the AP Chemistry course and exam description. The reaction quotient, QC, describes the relative concentrations of the reaction species at any time. For gas phase reactions, the reaction quotient may instead be written in terms of partial pressures as QP. So when you see the subscript C, that represents concentrations, and when you see the subscript P, that represents pressures. The reaction quotient, Q, tends toward the equilibrium constant K, such that at equilibrium, Q is equal to K. So if we're talking about concentrations, then QC is equal to KC at equilibrium. If we're talking about partial pressures, then QP is equal to KP at equilibrium. As examples for the chemical equation that shows the reactants A and B being converted into the products C and D, the equilibrium expression for Kc or QC is written as follows. Kc is equal to this ratio of products over reactants. Now, when you see a chemical formula inside hard brackets, the hard brackets represent concentration or the molarity of each of those substances. So we have products over reactants. It would be the concentration of the product C raised to the power of whatever that coefficient is for that substance in the chemical equation. And then times the concentration of the product D, again raised to the power of its coefficient from the chemical equation. In the denominator, it would be the concentration of the reactant A raised to the power of its coefficient from the chemical equation. And then also in the denominator, the concentration of the reactant B, again raised to the power of its coefficient from the chemical equation. So that is the generic representation of Kc, products over reactants, where hard brackets represent the concentration or the molarity of each substance. Now, moving on to partial pressures, the equilibrium expression for Kp or Qp is written as follows. We still have a ratio of products over reactants, but now we are not using hard brackets. Instead, you can see a capital letter P, which represents the partial pressure of each substance. So what I see here in that expression is the partial pressure of substance C, again raised to the power of its coefficient from the equation, times the partial pressure of substance D, again raised to the power of its coefficient from the chemical equation, and in the denominator we have the partial pressure of substance A raised to the power of its coefficient times the partial pressure of substance B raised to the power of its coefficient. Now, both of these expressions, Kc and Kp, will make a lot more sense once you practice writing these expressions for specific chemical equations, and that's coming up in this section of the packet. And then finally, the reaction quotient does not include substances whose concentrations or partial pressures are independent of the amount, such as for solids and pure liquids. That's another way of saying that solids and pure liquids do not appear in the equilibrium expression. On this slide, you can see the expression for the reaction quotient QC on the left and the reaction quotient QP on the right. So here is that generic chemical equation that I mentioned earlier, where the capital A and capital B are the reactants, and capital C and capital D are the products, and the lowercase letters A, B, C, and D are the coefficients in the chemical equation. So when we use hard brackets to surround the chemical formula of a substance, that symbol refers to the concentration of that substance in units of moles per liter. So here you can see products over reactants, where the concentration of each substance is raised to the power of its coefficient. So for QC, the subscript C indicates that concentration values, moles per liter, are used in the expression. And on the other side, you can see that that's the QP, where the subscript P indicates that pressure values are used in the expression. So we use a capital P and the subscript of the chemical formula of that substance that refers to the partial pressure of that substance in units of atmospheres. It's products over reactants, where each pressure is raised to the power of its coefficient in the chemical equation. And so now, if you take a look at this next slide, what you're looking at here is a portion of the AP Chemistry Equations and Constant sheet. This portion of the equation sheet is entitled Equilibrium. That is the title of Unit 7. Unit 7 is Equilibrium. So you can see I've highlighted on this slide the two equations that I mentioned in topic 7.3. We have the Kc expression, and you can see the hard brackets. The hard brackets represent the concentration or the molarity of each substance. And then there's also the Kp expression. That capital P for each substance represents the partial pressure, and that would be the partial pressure in units of atmospheres. So Kc, concentration, molarity of each substance; Kp, partial pressure, the pressure in atmospheres of each substance. Now, in case you're wondering, what about all of the other equations that are listed in this section of the equation sheet? Well, all of these other equations that you can see, those will be covered in Unit 8. Unit 8 is entitled Acids and Bases. So all of these other equations will be mentioned when we get to Unit 8. So what's the difference between the reaction quotient Q and the equilibrium constant expression K? Well, at some point when the system is at equilibrium, the value of Q is equal to the value of K, but the reaction quotient is evaluated at any point during the reaction. So you solve for Q by substituting in the values for the concentrations or partial pressures into the expression, and that would be at any point during the reaction. Whereas for the equilibrium constant expression, you would solve for K by substituting in the values for the concentrations or the partial pressures of the reactants and products when the system is at equilibrium. So at any point during the reaction, it's going to be the reaction quotient Q, and when the system is at equilibrium, it's the equilibrium constant K. All right, this is question 4 of the packet. The instructions are the following. For each of the following chemical equations, write the equilibrium constant expression for both Kc and Kp. Note that solids and pure liquids are not included in the reaction quotient or in the equilibrium constant expression K. In the first chemical equation, the reactants are nitrogen, N2, and hydrogen, H2, and the product is ammonia, NH3. To write the Kc expression, we're going to use hard brackets to represent the concentration of each substance. It will be products over reactants, and the concentration of each substance is raised to the power of its coefficient. So we have the concentration of ammonia squared divided by the product of the concentration of nitrogen times the concentration of hydrogen cubed. Now, as we switch from Kc to Kp, we replace the hard brackets symbol with capital P indicating partial pressure, and then the subscript would be the chemical formula of that substance. It'll still be products over reactants, and the pressure of each substance is raised to the power of its coefficient. So we have the partial pressure of ammonia squared divided by the product of the partial pressure of nitrogen times the partial pressure of hydrogen cubed. In our next chemical equation, we have sulfur trioxide, SO3, as the reactant, and the products are sulfur dioxide, SO2, and molecular oxygen, O2. So for the Kc, we're going to use hard brackets to represent the concentration of each substance, its products over reactants, and the concentration of each substance is raised to the power of its coefficient. So we have the concentration of sulfur dioxide squared times the concentration of oxygen divided by the concentration of sulfur trioxide squared. When we switch from Kc to Kp, we replace the hard brackets with a capital P for partial pressure of each substance. So it's going to be products over reactants, partial pressure of SO2 squared times the partial pressure of O2 divided by the partial pressure of SO3 squared. Now, in the next part of question 4, in these examples, I want to remind you that solids and pure liquids are not included in the reaction quotient or in the equilibrium constant expression K. So what I see in this next chemical equation is solid calcium carbonate, CaCO3. That's not going to be included. And solid calcium oxide, CaO, is also not going to be included. So all we have left in this expression is carbon dioxide, CO2. So the Kc is simply the concentration of CO2, and that's it. And the Kp is the partial pressure of CO2, and that's it. Now in our next example, the chemical that I see that is a solid is lead iodide, so we're not going to include that in the expression. So for the Kc, it's going to be concentration of the lead ion, so Pb2+, times the concentration of the iodide ion, I-, and that's going to be squared because the coefficient of 2 for the iodide in the chemical equation. There's no version of Kp for this particular equation because there are no gases present. Now for this last equation in the table, the pure liquid, water, is not going to be included in the expression. We'll do a Kc with products over reactants, so it's the concentration of the hydronium ion, H3O+, times the concentration of the fluoride ion, F-, divided by the concentration of hydrogen fluoride or hydrofluoric acid, HF, on the bottom. All right, let's move on to our next topic in this packet. This is topic 7.4, calculating the equilibrium constant. There is one brief essential knowledge statement from the AP Chemistry course and exam description, and that is equilibrium constants can be determined from experimental measurements of the concentrations or partial pressures of the reactants and products at equilibrium. Now let's take a look at question 5 in your packet. Question 5 says, a series of experiments was performed in the laboratory based on the reaction represented above, in which 1 mole of N2O4 decomposes into 2 moles of NO2. Each reaction was carried out at a temperature of 373 Kelvin. Part A. Calculate the change in concentration for each substance in each experiment. So we have 6 different tables, and they show the initial concentration of each substance. The change is what we have to come up with, and they show the concentration of each substance at equilibrium. So initial, change, and equilibrium is a very common feature. At some point later on in this video, I'll talk about something called a Rice table, where we have reaction, initial, change, and equilibrium in that table. So that's a little preview of what's coming up a little bit later. Now, you may be able to do a lot of these calculations in your head, but feel free to use a calculator for some of these. So experiment number 1, the difference between 10 and 9.3 is 0.7, so it's decreasing by 0.7, and the difference obviously between 0 and 1.4 is 1.4, so it's increasing by 1.4. In that experiment, we started with reactant only and no products initially. So the reactant went down by 0.7 and the product went up by 1.4. In experiment number 2, we start with no reactants and all products. So the change for the N2O4, the reactant, it increased by 4.51, and the change in the concentration of the product, NO2, it decreased from 10 to 0.98. That's a difference of 9.02. So the reactant increased by 4.51, and the product decreased by 9.02. Now in experiment 3, we have a little bit of both. We have 10 molar for both the reactant and the product concentration. And so we can see that in this example, the concentration of the reactant increased by 4.14, and the concentration of the product decreased by 8.28. Now moving on to experiment number 4, we can see that the concentration of the reactant increased by 2.46, and the concentration of the product decreased by 4.92. In experiment number 5, the concentration of the reactant decreased by 0.14, and the concentration of the product increased by 0.28. These are all concentration values. And then experiment 6, the concentration of the reactant increased by 1.10, and the concentration of the product decreased by 2.20. So you can see in the balanced chemical equation that we have an understood coefficient of 1 for the reactant, N2O4, and then we have a coefficient of 2 for the product, NO2. So 2 moles of NO2 are formed for every 1 mole of N2O4 that is consumed. And I'm highlighting the change. Hopefully you can see that the absolute value of the change in NO2 is twice as much as the absolute value of the change in N2O4. That's consistent with this 2-to-1 ratio from the coefficients in the balanced equation. So part B says the value for the ratio, the absolute value of the ratio of the change in NO2 over the change in N2O4 in all 6 experiments is equal to 2. And that's consistent with the coefficients that 2 moles of NO2 are produced for every 1 mole of N2O4 that is consumed. But if the reaction is going in the opposite direction, you can say that 2 moles of NO2 are consumed for every 1 mole of N2O4 that is produced. All right, in part C, now that we have determined all of the change, let's focus on that last row of the table, which is the amount present at equilibrium. Remember, Unit 7 is entitled Equilibrium, so here we have the equilibrium constant expression, concentration of the product, NO2, squared, divided by the concentration of the reactant, N2O4. I'll start with experiment number 1. In our experiment number 1, we have a concentration of NO2 of 1.4, so 1.4 squared, divided by the concentration of N2O4, which is 9.3. 1.4 squared divided by 9.3 is equal to 0.21. Now, for all the other experiments, I'll do the same procedure. Concentration of NO2 squared divided by the concentration of N2O4. And these are the equilibrium concentrations. So we're calculating Kc for each experiment at 373 Kelvin. And it does say to round off your answers to 2 significant figures. So for experiment 2, it's 0.98 squared divided by 4.51, and I get the same numerical value, 0.21. So hopefully we'll see if we can see a pattern here. Experiment 3, 1.72 squared divided by 14.14. So as you can do these calculations, I'll go a little bit faster here and I'll keep talking about it. You're going to take the concentration of NO2 squared divided by the concentration of N2O4, and we keep getting the same numerical value for the equilibrium constant. So what I'm showing you is that no matter whether the experiment began with all reactants and no products, or whether the experiment began with all products and no reactants, or whether the experiment began with a mixture of reactants and products, the final concentration of reactants and products at equilibrium, when plugged into the equilibrium constant expression, we get the same value. Now, if you're wondering, is this equilibrium constant ever going to change? And the answer is yes, but only if you change the temperature. So the value of the equilibrium constant for a particular reaction is normally calculated at a specific temperature. If you change the temperature at which the reaction is carried out, then the value of the equilibrium constant, K, should also change. All right, this is question 6. So question 6 says the following. The system represented by the equation above, in which hydrogen reacts with iodine to produce hydrogen iodide, this system reached equilibrium at 448 degrees Celsius. The concentrations of the substances in the reaction vessel at equilibrium were determined to be the following. So the concentration of hydrogen is 0.80 moles per liter. Concentration of iodine is 0.54 moles per liter. And the concentration of hydrogen iodide is 4.7 moles per liter. Part A. Calculate the value of the equilibrium constant, Kc, for this system at 448 degrees Celsius. Round off your answer to 2 significant figures. So the first thing we're going to do is write the equilibrium constant expression for this reaction. That's going to be products over reactants, and we're going to use hard brackets because this is concentration, Kc. So concentration of hydrogen iodide squared divided by the product of the concentration of hydrogen times the concentration of iodine. Now we can calculate the value of the equilibrium constant by using these concentration values which were present in the reaction vessel at equilibrium. So 4.7 for the concentration of hydrogen iodide squared divided by the product of 0.80 times 0.54. And when we do this math on our calculator, we get 51.134. Rounding this off to 2 significant figures, it'll be 51. Now, interestingly enough, there are actually no units that are used for the equilibrium constant or the reaction quotient. They are dimensionless quantities and do not have units. And the reason why has to do with a procedure where each concentration or each partial pressure is divided by a reference factor. So for concentration, each concentration is divided by 1 mole per liter, and for pressure, each pressure is divided by 1 atmosphere. So the units completely go away. So when you write an equilibrium constant expression, it's always moles per liter for concentration, Kc, and it's always pressure in atmospheres for Kp, but the final numerical answer does not have any units. All right, now that we know that the value of Kc for this particular reaction at 448 degrees Celsius is 51, let's move on to part B of this question. Part B says the following. In a separate experiment, samples of hydrogen and iodine were added to a previously evacuated reaction vessel with an initial concentration of 0.25 molar for each substance. The reaction was allowed to proceed at 448 degrees Celsius until the system reached equilibrium. Should the concentration of hydrogen in the reaction vessel at equilibrium be less than or greater than 0.25 moles per liter? Justify your answer. Now, in this experiment, we're not starting off with a mixture of both reactants and products. We're starting off with a mixture of reactants only. We have hydrogen and iodine, and that's it. The concentration of hydrogen and iodine are 0.25 moles per liter, but because there is no hydrogen iodide present at time 0, its initial concentration is 0. This reaction would have to proceed from left to right, from reactants to products, in order to reach equilibrium. So some of the hydrogen is going to be consumed as we approach equilibrium. So at the beginning of this experiment, there is no hydrogen iodide present in the reaction vessel. There is only hydrogen and iodine. And since the forward reaction will proceed to reach equilibrium, consuming some of the hydrogen, therefore the concentration of hydrogen at equilibrium should be less than 0.25 moles per liter. All right, in part C, now we are given information about concentration, and we're not necessarily at equilibrium. It says another experiment was performed with this system, and at a certain point in time, the concentrations of the substances in the reaction vessel at 448 degrees Celsius were determined to be the following: concentration of hydrogen 0.15 molar, concentration of iodine 0.25 molar, and concentration of hydrogen iodide 3.2 molar. Remember that the reaction quotient is something that you can evaluate at any point during the reaction. So that's what we're going to do right now. We're going to calculate the reaction quotient. So with the concentrations listed above, is this system at equilibrium? Justify your answer by calculating the value of the reaction quotient for this system at 448 degrees Celsius. So our expression for QC is the same as the expression for KC. It's products over reactants, concentration of hydrogen iodide squared, divided by the product of the concentration of hydrogen and iodine. Now, if we get a value of 51, then that means we are at equilibrium. Let's take a look. 3.2 is the concentration of hydrogen iodide, so 3.2 squared, divided by the product of 0.15 times 0.25. So on our calculator, we get 273 for the reaction quotient. So we are not at equilibrium. This system is not at equilibrium because QC, 273, is not equal to KC, 51. Now, part D of this question is a follow-up to part C. So we've already calculated that QC equals 273, and we've established that we're not at equilibrium yet. In which direction? Toward the left, reactants, or toward the right, products, should the reaction proceed in order to achieve equilibrium? Justify your answer. Remember that it's products over reactants for this reaction quotient or the equilibrium constant. So if we shift toward the products, if the reaction continues to proceed toward the products, then the value of Q is going to get larger and larger and larger. If we proceed toward the reactants, then that will cause the value of Q to get smaller as some of the products are consumed and additional reactants are formed. So I'm thinking we should go toward the left. Let's take a look at the answer. Since the value of Q, which is 273, is larger than the value of K, 51, it appears that there are too many products, or not enough reactants. In order for the value of Q to decrease, the reverse reaction, as in from right to left, should proceed. So toward the left until eventually the value of Q equals K. Now, before I talk about question 7 in your packet, I'd like to spend some time discussing this situation of comparing Q, the reaction quotient, with K, the equilibrium constant. So suppose that you already know the value of the equilibrium constant, K, for a certain reaction at a certain temperature. And suppose that you also know the values for the concentrations or partial pressures of the reactants and the products at a certain point in time. You can calculate the value of the reaction quotient Q, and then what you do is you compare Q with K. So when you compare Q with K, you can determine which one of the following situations is true. If Q is equal to K, then the system has already reached equilibrium. If instead the Q is less than K, then that means that there are too many reactants or not enough products. So a net conversion of reactants to products from left to right would occur until the equilibrium is achieved and Q equals K. If, on the other hand, Q is greater than K, then there are too many products or not enough reactants. A net conversion of products to reactants from right to left occurs until equilibrium is achieved and Q equals K. So here are some mnemonic devices to help you remember the consequences of Q versus K. So if Q is less than K, then you can think of the ratio of products over reactants as the following, where the numerator is too small and the denominator is too big. In other words, we have too many reactants on the bottom or not enough products on the top. That might help you decide we need to make more products and consume some of the reactants. In this next mnemonic device, the inequality symbol, the greater than or the less than symbol, is used as an arrow, but you have to set it up in such a way that K is written before Q. So you can think of it in alphabetical order. Put K before Q. Now watch what happens. If Q is less than K, the inequality symbol points you in the direction in which there has to be a net conversion from reactants to products or from left to right until eventually equilibrium is achieved and Q equals K. Now let's consider the other example. What if Q is greater than K? You can set up your ratio of products over reactants where you have a large numerator and a small denominator. In other words, there's too many products or not enough reactants, and we're going to have to proceed from right to left to either consume some of the extra products or form more reactants. Same with that inequality symbol. If K is written before Q, and if Q is greater than K, then the inequality symbol points as an arrow that there should be a net conversion from products to reactants or from right to left until equilibrium is achieved and Q is equal to K. All right, so question 7 is exactly that idea of comparing Q with K. So we have 3 scenarios, number 1, number 2, and number 3. For each set of experimental conditions listed in the table below, use the data to calculate the value of the reaction quotient, QC. Now, we already know that the Kc for this reaction at this temperature is 51. So compare Kc with QC and then choose one of the following consequences. The system is already at equilibrium, or the system should proceed toward the products from left to right until equilibrium is achieved, or the system should proceed toward the reactants from right to left until equilibrium is achieved. Let's take a look at our first example. This is situation number 1, and we have concentrations of 0.35 for hydrogen, 0.45 for iodine, and 3.0 for hydrogen iodide. These are all concentrations, moles per liter. So the Q, the reaction quotient, is 3 squared divided by the product of 0.35 times 0.45. Now we get a number which is 57. So clearly 57 is larger than 51. So Q is greater than K. And that little inequality symbol, as you can see, the way I've set it up, is pointing toward the left or toward the reactants. So when Q is larger than K, we have too many products or not enough reactants. So what's the consequence? The system should proceed toward the reactants from right to left until equilibrium is achieved. In our next example, we'll do the same calculation of products over reactants. So the concentration of hydrogen iodide is 4.2, so 4.2 squared, divided by the product of the concentrations of hydrogen and iodine, which are 1.6 and 1.4. So 4.2 squared divided by the product of 1.6 times 1.4, we get 7.9. So clearly 7.9 is less than 51. So Q is less than K. And so as we're setting this up, we can see that if Q is less than K, the inequality arrow is pointing toward the right, toward the products. If Q is less than K, you have too many reactants or not enough products. The consequence is that the system should proceed from left to right toward the products until eventually equilibrium is achieved and Q equals K. And now you can probably anticipate what this third scenario is. We have to take the products over reactants, 6.1 squared, divided by the product of 0.9 times 0.81. And when we plug in those numbers into the equilibrium expression for the reaction quotient, we get 6.1 squared divided by the product of 0.9 times 0.81. And look at that. It's exactly 51. Q equals K. There is not going to be any proceeding toward the left or proceeding toward the right because the system is already at equilibrium. This is question 8 in your packet. It says, consider the system represented by the equation above. And we see a balanced equation in which 1 mole of COCl2 decomposes to produce 1 mole of CO and 1 mole of Cl2. A sample of pure COCl2 is added to a previously evacuated rigid reaction vessel at 690 Kelvin. The initial pressure in the reaction vessel before any reaction occurs is 1.0 atmospheres. After the system has reached equilibrium at 690 Kelvin, the total pressure in the reaction vessel is 1.2 atmospheres. Part A, determine the partial pressure of each substance in the reaction vessel at equilibrium. Now, at first glance, it might seem like question 8 is too challenging or difficult to solve. You might be thinking, how am I supposed to determine the partial pressure of each substance in the reaction vessel at equilibrium? And how am I supposed to calculate the value of the equilibrium constant Kp for this reaction at 690 Kelvin? Well, one of the reasons that makes question 8 a challenging problem is it seems like you don't have enough information to do the various calculations for partial pressure or the equilibrium constant Kp. And this type of question is easier to solve if you create what is known as a Rice table, where the word Rice is an acronym which represents the words reaction, initial, change, and equilibrium. So the first row of the Rice table represents the reaction or the balanced chemical equation. And then the next row of the Rice table represents the initial conditions, and these could be the initial concentrations or partial pressures of each substance at the very beginning before any chemical reaction has occurred. Then we have the change row of the Rice table, in which certain concentrations or partial pressures will either increase or decrease depending on the conditions. And then finally, the last row of the Rice table would be equilibrium. So when equilibrium has been achieved, what are the values for either the concentration or the partial pressure of each substance? So let's begin. Based on the information that we have, what are the initial conditions? And it says that a sample of pure COCl2 gas is added to a previously evacuated rigid reaction vessel at 690 Kelvin. Now, since COCl2 is the only gas that was mentioned, that was added to this reaction vessel, we can assume that at the very beginning, there is no carbon monoxide, or CO, and there is no chlorine, or Cl2, present in the reaction vessel. And if the initial pressure in the reaction vessel is 1 atmosphere, then that would be the partial pressure of the only gas that was added to this reaction vessel. So we can assume that the partial pressure of CO and Cl2 would be 0 before any reaction occurs. Now let's move on to the change row of this Rice table. Since the only chemical that is present initially is the reactant, COCl2, then we know that there must be a net conversion from reactants to products. Therefore, as this reaction proceeds, the pressure of COCl2 must decrease, and the pressure of the products, CO and Cl2, must increase. Now, what we're going to do is represent these changes in terms of x. So we're going to let x represent the magnitude of change in pressure. And since all of the coefficients are equal to 1, that means that the change will either be minus x or plus x, depending on whether or not it's decreasing or increasing. So the pressure of the COCl2 is going to decrease, so we'll say minus x, and then the pressure of the CO and the Cl2 are going to increase, so we can say plus x and plus x. And when you are filling in the information in the change row of the rice table, that change in the amount of each substance, whether that's in terms of concentration or partial pressure, should be proportional to the coefficients in the balanced equation. So because the coefficients are 1, 1, and 1, that's why the change is going to be in terms of x, x, and x. We'll see in other examples in this packet that it might be 2x or 3x, depending on what the coefficients in the balanced equation happen to be. Now we have to fill out, in terms of x, the information in that final row of the rice table. So what are the partial pressures of each gas in terms of x? So for the COCl2, that would be 1 minus x, and for the CO and the Cl2, that would be x and x. The next thing that we're going to do is remember something that you learned when we were studying about the properties of gases. And that is that the total pressure of a gas mixture is going to be equal to the sum of the partial pressures of the individual gases in the mixture. So we know that at equilibrium, the total pressure in the reaction vessel is equal to 1.2 atmospheres. Here, on the AP Chemistry Equations and Constant sheet, this is the section entitled Gases, Liquids, and Solutions. You can see that the equation for the total pressure of a gas mixture, P total, is the sum of the partial pressures of the individual gases in the mixture. So now let's go ahead and set equal to 1.2 atmospheres the sum of 1 minus x and x and x. So now we have an algebraic equation. 1 minus x plus x plus x is equal to the total pressure of 1.2 atmospheres. All we have to do now is solve for x. So 1 minus x plus x, that will equal 1 plus x. We set that equal to the total pressure that we were given, which is 1.2 atmospheres, and hopefully you can see that the value of x is equal to 0.2. Well, now that we know that x equals 0.2, we can fill in the remainder of this rice table with actual numbers. So the change row of the rice table now becomes minus 0.2, plus 0.2, plus 0.2. And so once this system has reached equilibrium at 690 Kelvin, the partial pressure of COCl2 is equal to 1 minus 0.2, or 0.8 atmospheres, and the partial pressure of CO and Cl2 would be 0.2 atmospheres for each of those gases. Hopefully you can see how making a rice table made this much easier to solve. So we have now answered Part A of question 8. Determine the partial pressure of each substance in the reaction vessel at equilibrium, and you can see highlighted in yellow, those are the partial pressures of each substance in the reaction vessel. Now let's move on to Part B. Calculate the value of the equilibrium constant, Kp, for the reaction at 690 Kelvin. So here is the Kp expression. It's going to be products over reactants, and because it's Kp, we're going to do this in terms of partial pressure. where the partial pressure of each gas is in units of atmospheres. So we have the partial pressure of CO times the partial pressure of Cl2 divided by the partial pressure of CoCl2. And all of these are raised to the first power because all of the coefficients are 1. So 0.2 times 0.2 divided by 0.8. Remember that the equilibrium constant is a dimensionless quantity, so we don't need to include any units in our answer. So if we do that math of 0.2 times 0.2 divided by 0.8, we get the answer to part B, that the value of the equilibrium constant Kp for the reaction at 690 Kelvin is equal to 0.05. Now let's take a look at question 9. In question 9, we are given a balanced chemical equation, and it says, consider the system represented by the equation above. Samples of all three substances were added to a previously evacuated rigid reaction vessel at 300 Kelvin. The initial values for the partial pressures of the substances in the reaction vessel were determined to be the following. The partial pressure of nitrogen gas, N2, is equal to 6.7 atmospheres. The partial pressure of hydrogen gas, or H2, is equal to 6.0 atmospheres. And the partial pressure of ammonia, or NH3, is equal to 0.2 atmospheres. After the system has reached equilibrium at 300 Kelvin, the partial pressure of the ammonia gas is 1.4 atmospheres. So question 9 is similar to question 8 in that we have to answer those same questions. First, determine the partial pressure of each substance in the reaction vessel at equilibrium, and then calculate the value of the equilibrium constant Kp for the reaction at 300 Kelvin. And it says, hint, create a rice table to solve this problem. So let's go ahead and do that. The first row of the rice table is the reaction. So we have our balanced chemical equation involving nitrogen reacting with hydrogen to produce ammonia. And for the initial values for the partial pressure of each gas, these were given to us as 6.7 atmospheres for the partial pressure of nitrogen, 6.0 atmospheres for the partial pressure of hydrogen, and 0.2 atmospheres for the partial pressure of ammonia. Now we are given one more piece of information, and that is after the system has reached equilibrium at 300 Kelvin, the partial pressure of ammonia is 1.4 atmospheres. Hopefully you can see that there was an increase in the partial pressure of ammonia, so that means that there must have been a net conversion from reactants to products. So what I mean by that is that the partial pressures of the nitrogen and the hydrogen must have decreased because those are the reactants, and the partial pressure of the ammonia, as we can see, must have increased from 0.2 to 1.4. Now let's go ahead and just consider the words decrease and increase. So the partial pressure of the nitrogen and the partial pressure of the hydrogen, which are the reactants, they would have decreased, and the partial pressure of the ammonia, which is a product, must have increased. What I'm going to do now is use X to represent the quantity of change, but unlike question 8, where the coefficients were 1, 1, and 1, as you can see in this balanced chemical equation, the coefficients from left to right are 1, 3, and 2. And so that's why the magnitude of change in terms of X is X, 3X, and 2X. So as you can see highlighted on this slide, when you are filling in the information in the change row of the rice table, the change in the amount of each substance in concentration or in pressure should be proportional to the coefficients in the balanced equation. So how did I know that it was minus X or plus X or minus 3X or plus 3X? remember that the reactants are going to decrease and the product is going to increase because we knew that the pressure of ammonia changes from 0.2 atmospheres to 1.4 atmospheres. So there's going to be a decrease in the partial pressure of the reactants and an increase in the partial pressure of the product. But it's going to be proportional to the coefficients. So minus x, minus 3x, and plus 2x. All we have to do now is solve for x. So since 2x, which represents the change in the partial pressure of ammonia, and that equals 1.2, if 2x equals 1.2, that means that x is equal to 0.6. Now that we know that x is equal to 0.6, we can fill in the remainder of this rice table with actual numbers. So minus x becomes minus 0.6 atmospheres, minus 3x becomes minus 1.8 atmospheres, and then plus 2x becomes plus 1.2 atmospheres. The final row of the rice table, the equilibrium partial pressures of all three of these substances, 6.7 minus 0.6 is equal to 6.1 atmospheres. So that value is the partial pressure of nitrogen at equilibrium. 6.0 minus 1.8 is equal to 4.2 atmospheres. So that value is the partial pressure of hydrogen at equilibrium, and then we already know that at equilibrium, the partial pressure of ammonia is 1.4 atmospheres. So we have now used our rice table to answer part A of question 9. Now for part B, let's begin by writing the equilibrium constant expression, Kp, for this particular reaction. So it's going to be products over reactants. Because it's Kp, we're doing this in terms of partial pressure. And then we do have coefficients to worry about, which means that the partial pressure of each gas is raised to the power of its coefficient from the balanced chemical equation. So products over reactants. The partial pressure of ammonia squared, because the coefficient for ammonia is 2 in the chemical equation. And in the denominator, we have the partial pressure of nitrogen times the partial pressure of hydrogen cubed. Again, raised to the third power because the coefficient for hydrogen is 3 in the chemical equation. Let's plug in our actual values for the partial pressure of each gas, and it looks like this. 1.4 atmospheres squared. We're not going to use any units because remember that the equilibrium constant K, whether that's Kc or Kp, is a dimensionless quantity that has no units. So 1.4 squared divided by the product of the following, which is 6.1 times 4.2 cubed. So if we plug that information into our calculator, we get a value of 0.0043. So that is the answer to part B. The value of the equilibrium constant, Kp, for the reaction at 300 Kelvin is equal to 0.0043. Or you could also write that number in scientific notation as 4.3 times 10 to the negative 3. So again, those are the answers to question 9. Now let's take a look at our next topic in the packet. This is topic 7.5. Magnitude of the equilibrium constant. Here is a very brief essential knowledge statement from the AP Chemistry course and exam description. Some equilibrium reactions have very large K values and proceed essentially to completion. Others have very small K values and barely proceed at all. To see examples of this, let's start looking at questions 10 and 11 in your packet. So here is question 10. We are given a balanced chemical equation, and we are also given the equilibrium constant Kp, which has a value of 6.4 times 10 to the 9. So again, this would fall under the category of a very large K value and would proceed essentially to completion. Question 10 says, when the reaction represented by the equation above reaches equilibrium, which of the following substances, NO or NO2, should have a higher value for partial pressure in the reaction vessel? Circle your choice and justify your answer. So with a rather large K value, the products are going to be favored at equilibrium. This reaction goes essentially to completion from left to right. So at equilibrium, there should be a much greater amount of the product than there is of the reactant. Now let's compare what we saw in question 10 with the situation in question 11. So here we are given a balanced chemical equation, and the value of the equilibrium constant Kc is 6.2 times 10 to the negative 10. So this is actually a very small number, as opposed to in question 10 we had a very large value of K. So now we have to decide which of the following substances, HCN or Cn-, should have a higher concentration when this reaction reaches equilibrium. So since the value of Kc is very small, the reverse reaction essentially goes to completion. So we are favoring the reactants at equilibrium instead of favoring the products. So to summarize what you have seen in questions 10 and 11, here is question 12. When the value of the equilibrium constant K is very small, as we saw in question 11, the reactants are favored at equilibrium. But when the value of the equilibrium constant K is very large, as we saw in question 10, the products are favored at equilibrium. Now let's take a look at question 13. In question 13, we are given a balanced chemical equation, and we are also given the value of the equilibrium constant Kc for this reaction at 1200 Kelvin. In question 13, it says, samples of CH4 and H2S are introduced into a previously evacuated rigid container. The initial concentrations of these substances are the following. The concentration of CH4 is equal to 0.30 molar or 0.30 moles per liter, and the concentration of H2S is equal to 1.0 molar or 1.0 moles per liter. The temperature is held constant as the reaction, represented by the equation above, reaches equilibrium at 1200 Kelvin. Part A. Considering the value of the equilibrium constant, Kc, calculate the final concentration of H2S, CS2, and H2 in the reaction vessel after the system reaches equilibrium at 1200 Kelvin. So as you can imagine, as we had done earlier in questions 8 and 9, let's go ahead and use that strategy of creating a rice table and filling in as much of the information as we can. So the first row of our rice table is the reaction. So there is the balanced chemical equation for this reaction. And now, what are the initial concentrations of these substances? So we are told that the initial concentration of CH4 is 0.30 moles per liter, and the initial concentration of H2S is 1.0 moles per liter. So we can assume that because we're not given any information at all about the products CS2 and H2, that those initial concentrations are 0 before any reaction occurs. Now, with respect to the change, let's think about increase and decrease for a moment before we fill in the change row of the rice table. Since all we have initially are reactants and no products, there must be a net conversion from reactants to products. And so that means that the concentration of CH4 and H2S must decrease as this reaction proceeds, and the concentration of the products CS2 and H2 must increase as this reaction proceeds. But now what I'm going to do is write the change row of the Rice table in terms of the variable x. So I have minus x for CH4 because its coefficient is 1. And since the coefficient of H2S is 2, I'm going to write minus 2x. Again, those are the concentrations that should decrease. So minus x and minus 2x. Remember that when you're filling in the information in the change row of the Rice table, the change in the amount of each substance in concentration or pressure should be proportional to the coefficients in the balanced equation. Now, moving on to the product side, we know that the concentration of the products are going to increase, so it's going to be plus x for the CS2, which has a coefficient of 1. But since the coefficient for the hydrogen is 4, then that change will be plus 4x. So in terms of x, because we have coefficients of 1, 2, 1, and 4, you can see that those x terms are x, 2x, x, and 4x. Again, minus x and minus 2x because the concentration of the reactants will be decreasing over time, and plus x and plus 4x because the concentration of the products will be increasing over time. Now let's fill in the final row of the Rice table in terms of x. So 0.3 minus x, 1.0 minus 2x, and then we have x and 4x. You might be a little concerned at this point. I'm going to go ahead and write the equilibrium constant expression, products over reactants. So we have the concentration of CS2 times the concentration of hydrogen raised to the 4th power. Again, that would be the products. I'm using the coefficient of 4 as an exponent for the hydrogen. And in the denominator of this Kc expression, I have the concentration of CH4, and I have the concentration of H2S squared, or raised to the 2nd power, because it has a coefficient of 2. Again, you might be a little concerned, how are we supposed to solve for x with such a complicated expression? And so the answer is, there's got to be an easier way. There must be an easier way to solve this Rice table because the math clearly is too complex for us to solve. Remember, this is topic 7.5, magnitude of the equilibrium constant. And the essential knowledge statement says some equilibrium reactions have very large K values and proceed essentially to completion. Take a look at that value of the equilibrium constant Kc for this reaction in question 13. It's 3.3 times 10 to the 4. That is a rather large value. So in part A of question 13, it said, considering the value of Kc, calculate the final concentration of H2S, CS2, and H2 in the reaction vessel after the system reaches equilibrium. So since the value of Kc is very large, we can assume that this reaction proceeds essentially to completion. So we can treat this as a limiting reactant problem. Now, this reaction will proceed until one of the reactants is essentially reduced all the way down to 0. Approximately 0 is really what's going on. So I have 0.30 moles per liter for CH4. That's going to decrease to essentially 0. Now, what about the H2S? Well, the change should be twice as much compared to CH4 because the H2S has a coefficient of 2. Remember, we saw minus x and minus 2x. So it's going to be minus 0.30 and then minus 0.60. So the H2S is not the limiting reactant because there is still an excess amount of H2S that would remain if this reaction proceeds essentially to completion. So what I have so far is at equilibrium, the concentration of CH4 is very small, approximately 0. The concentration of H2S, which was reduced by 0.6, is now 0.40 moles per liter. Let's consider what happens for the products. So I have to increase as opposed to decrease the concentration. So it's going to be plus 0.30 because it has a coefficient of 1. Again, that coefficient of 1 matches the coefficient of CH4, which is also 1. But considering that the hydrogen has a coefficient of 4, that means that the change for hydrogen would be 4 times as much as the change for CS2. So 0.3 times 4 is 1.2. So if you look at the change row of the rice table, all of those changes are in proportion to the coefficients of 1, 2, 1, and 4. Well, now, as you can see, we have actually answered part A of question 13. Let's go ahead and move on to part B of question 13, which says, the final concentration of CH4 in the reaction vessel at equilibrium is very small, but not exactly 0. Calculate the concentration of CH4 at equilibrium. So what I'm going to do is write the equilibrium constant expression, Kc, and that would be products over reactants. I'm using hard brackets to represent the concentration of each substance. So in the numerator, we have concentration of CS2 times the concentration of H2 raised to the 4th power. In the denominator, we have the concentration of CH4 times the concentration of H2S raised to the 2nd power. We know all of these concentrations from our rice table except for CH4. So for the CS2, that would be 0.30. For the hydrogen, that would be 1.2. And then for the H2S, that would be 0.4. So all I did was I plugged in the equilibrium concentrations of everything that we know at this point, except for the CH4. So what it's telling us in part B is that the final concentration of CH4 is a very small number, but not exactly 0. I'm going to rearrange this equation. Again, I set this equal to the value of Kc, which is 3.3 times 10 to the 4. And as I rearrange this equation, I'm going to get the concentration of CH4 on one side of the equation. So here is the information I have to put into my calculator. 0.3 times 1.2 raised to the 4th power, and then divided by the product of the following. 3.3 times 10 to the 4th power times 0.4 squared. So if I put all of that information into my calculator, what I should get is a small number that is not exactly 0. So the concentration of CH4 at equilibrium is, in fact, a small number. So the number I got in my calculator was 1.2 times 10 to the negative 4. So that is the answer to part B of question 13. This is also the last question in this packet. So we are now at the end of this video. I hope that you found all of these answers and explanations helpful. Thanks for watching.